Hello and welcome everybody. Today's lesson is about geometry of molecules. If you ask yourself, like if we look at water molecule, ammonia, for example, or CH4, if we ask you like what are the geometries, they have different geometries, different shapes. And did you ask yourself why do they have different shapes? For example, that these things will be covered later, like why H2O looks like a V shape, why ammonia looks like pyramid. So we're going to start learning about every single detail, all of these cases. Let's start with water molecule. Okay, by the way, we're going to cover all of these details about how to draw these molecules. Before we start, if we look at this molecule, you can see that you have a water molecule, which is H2O. It's represented by oxygen atom with two pairs of electrons. You have a bond in here and another one. And as you remember something, since you're dealing with electrons, if we have two electrons, for example, they close to each other, you expect to have repulsion between them. And at that point, the geometry of this molecule won't be stable as a result of this repulsion. And actually, we have three types of repulsion within the molecule. So let's start with the first one, which is the strongest part or the strongest type of repulsion, which is between the lone pair. The lone pair of electrons, as we can see, they are the non-bonding electrons. Actually, they're presented in here, they're not bonded to anything, and they close to each other, and they have a great repulsion in here, and that's why we can put the repulsion strength here as number 1. And the second type of repulsion, which is represented between the lone pair and the electrons that are in the bond. If you go flashback and just remember that the covalent bond is a shared pair of electrons, and that's why you can say that you have electron in here and another electron from hydrogen and another electron from oxygen. And that's why we have another repulsion between the lone pair and the electrons and the bonds. And from the strength, like it comes after the repulsion, which is in here, and actually it takes the second order. And now the last one, which is the weakest type of repulsion, which is between the bonding electrons. You have a bond here, it contains electrons. You have another bond here, it contains electrons. We have repulsion between them, and that's why it's ordered by 3, or let's say the third place. How can I determine the shape of molecule based on these type of repulsion, what we call them, what are the angles, etc., etc. And now let's start with the case number 1, in which you have 2 bonds, okay, but no lone pairs. And now let's start with a beautiful example in which we have, for example, like BeCl2 molecule. How can I draw this molecule? The first thing is determining the central atoms. That looks like in the center, it's beryllium, Be. And now you have to remember at which group does the Be element belong to. And actually it belongs to group number 2 in the periodic table. However, this indicates that we have 2 electrons in the last shell or in the outermost shell. Okay. Which means that I have to represent these electrons in a form of dots in here. And by the way, the form of dots here is called Lewis structure. Lewis structure. So if you have heard about something like that, actually it's represented by dots and stuff. All right, how many atoms around the Be? We have 2 atoms, which are Cl. And you have to put in your mind the Cl atom, actually it's in group number 7, which means that it has 7 electrons in its outer shell. Cl, 1, 2, 3, 4, 5, 6, 7. And here we have another one, Cl, 1, 2, 3, 4, 5, 6, 7. And at that point, we can represent like the 2 electrons here are shared together, like here. And it will give us this form, Be, Cl, 1, 2, 3, 4, 5, 6, Cl, 1, 2, 3, 4, 5, 6. And at that point, you have to look at the central atom. First of all, do we have any electrons in the central atom? Here, we don't have anything. Then we don't have lone pairs at that point. Okay. How many bonds we have? We have the first one, here we have the second one. So at that point, if you have a compound that contains 2 bonds and 0 lone pairs, what do we call this shape? It's called linear shape. And the angle between the Cl, Be, Cl is 180 degrees. Okay, And now let's go to the second case in which we have two bonds, but in the presence of a lone pair. Okay, let's take an example, which is the one that we started with, which was H2O. As we can see, oxygen here represents the central atom because it's bonded to two hydrogen atom, and that's why it's a central atom. So we start with the first one, which is oxygen atom. And we just remember something, that oxygen locates in the group number 6, and it has 6 electrons in the outer shell. And that's why we have to draw like 1, 2, 3, 4, 5, 6. And we have two hydrogen atoms, and that's why those hydrogen, like in group number 1, they have only 1 electron, and that's why it's bonded like this at that form. And I just want to recover again, we have lone pair in here, we have another lone pair, and that's why you can say that the water molecule contains two lone pairs. Each lone pair contains 2 electrons. We have lone pairs and we have 2 bonds at that point. So what we call the shape of a molecule that contains 2 bonds in the presence of a lone pair, we call it V-shaped or nonlinear, okay, or bent. Okay. And by the way, the angle in water molecule between the hydrogen here is 104.5 degrees. And now let's go to the third case in which we have 3 bonds, okay, and no lone pairs. How can I do it? Let's start with BF3. The first thing here is determining the central atom, and the central atom here is B, which is boron, and actually it's in the group number 3 in the periodic table, and actually it has 3 electrons in its outer shell. And the fluorine atoms here are in the group number 7, and they have 7 electrons in their outer shell, and that's why we can say, okay, B here, we can put 3 electrons like 1, 2, 3, for example. And then we have fluorine atoms, we have F, it has 7 electrons in its outer shell. We have 1, 2, 3, 4, 5, 6, 7, another F, 1, 2, 3, 4, 5, 6, 7, and the third one, 1, 2, 3, 4, 5, 6, 7. And at that point, you can say that we have a single bond here, we have another single bond here, and we have another one. And that's why if we want to represent this in the lowest structural form, we have B, and we have F, F, and F. We have lone pairs in them. All right, at that point, the question number 1, do we have lone pairs in the central atom? No, we don't have lone pairs. How many bonds we have? We have 3. So what do we call the molecule when it has 3 bonds with no lone pairs? We call it a trigonal planar. Trigonal planar. Okay, and actually it looks like a spinner or the Mercedes sign, okay? And the angle for sure is 120 degrees in all of the molecule. Let's go to case number 4. Case number 4 says that if you have 3 bonds, but in the presence of a lone pair, we have a lone pair. And by the way, this is represented by a simple molecule, which is NH3, and it's called ammonia. How can I draw ammonia? Nitrogen is in a group number 5, and hydrogen is a group number 1, and that's why if we want to draw the nitrogen atom, we draw 5 electrons around it because it's in group number 5. We have to say 1, 2, 3, 4, 5. All right. We have hydrogen atoms. How many hydrogens we have? We have 3, and that's why you have 1, 2, and 3. So at this point, we have 3 bonds. 1, 2, 3 bonds, okay. And we have lone pair, yes. What do we call the molecule when it has 3 bonds in the presence of a lone pair? It's called trigonal pyramidal. Trigonal pyramidal. Okay, and by the way, it looks like a pyramid in which we have something like this. Yes, in which we have N, here we have hydrogens, you can see. You can imagine that if you use your power of imagination. And by the way, if you ask yourself about the angle between hydrogen, nitrogen, hydrogen, and actually in ammonia molecule, it's 107 degrees. And now let's go to the 5th case in our class, which is You have 4 bonds and no lone pair. So let's take a beautiful example in which we have CH4, which is methane gas. It's a flammable, and let's start. So the first thing here is determining the central atom. Since you have 4 hydrogen with respect to only 1 carbon atom, then the carbon is a central atom, and actually it's in group number 4, which means it has 4 electrons in outer shell. We have 1, 2, 3, 4. All right, how many hydrogens? We have 4 hydrogens. You have hydrogen here, another hydrogen here, another one here, another one here, and then it looks like CH4, like this. By the way, if you look at this shape, you'll say like, oh, it's normal. It looks like a 90 degrees shape, but actually it doesn't look like this. Actually, it looks like C, you have one here, and you have like this. So this is the shape of a molecule of methane. You have 4 bonds. You don't have any electrons on the central atom. We call this shape tetrahedral. Okay, tetrahedral. Angle of 109.5 degrees. And yeah, this is the tetrahedral. You could have something like, for example, like CCl4. Actually, it looks like the same, in which you have the carbon, which is a central atom. It has 4 electrons. And you could have SiCl4. Actually, it's the same idea, in which you have the silicon atom is in group number 4. So since in group number 4 it has 4 electrons, it means 4 bonds, no electrons in the central atom, then it's tetrahedral. Now let's go to case number 6, in which you have 5 bonds, okay, and no lone pairs, and actually it's represented by a famous example, which is PCl5. And the first thing is determining the central atom, and you can see this is a phosphorus. It's in group number 5, which means that it has 5 electrons in its outer shell. So we have to say P. You have 1, 2, 3, 4, 5. How many Cl you have? You have 5 Cl. Then you have Cl 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. If we translate these in terms of bonds, then it looks like P. You have bond here, okay, and one above and one down. So at this point you have Cl, okay, you have another one. We're drawing those in the form of a loose structure, in which you have those dots, as we can see. Okay, and now the question is, what we call this shape is here, what we call it? First of all, how many bonds you have? You have 5 bonds. And we don't have a lone pair, and that's why we call this shape a beautiful name. It's called a trigonal bipyramidal. And why we call it trigonal bipyramidal? Actually, it looks a spinner. It looks like a spinner in here. Okay, and we have another like a triangle in here, so that's why it's called bipyramidal. Bi here indicates to 2 pyramids over each other, and they have a base of a triangle, and that's why it looks like this, if you just like have an imagination about this one here. And now let's go to the last case, in which we have a 6 bonds, and for sure no lone pairs. And let's go. How can I do it? SF6. And actually, you have to find the central atom, which is sulfur. It's in group number 6, which means it has 6 electrons in its outer shell. So we have to say 1, 2, 3, 4, 5, 6, right? The fluorine atom, you know, like it's in group number 7 here. And you have to draw F, 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 F. And you draw the electrons around them, as we just remember. I just want to redraw it again in terms of a, let's say, a more organized stuff. You have S, and here you have F, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You ask me, where is the 7th electron? Actually, it's in the bonding in here, you know, like this is a sharing process. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And you have to put in your mind, we call this molecule when you have 6 bonds with no lone pairs. It's called octahedral. And by the way, if you ask yourself, like, how does it look like? It looks like two pyramids with square base, and like they are all above each other. And by the way, it looks like this. We call it octahedral, and all of the angles are 90 degrees. In here, if you go here for the phosphorus, put in your mind, since you have something that looks like a spinner in here, I just want to shade it a little bit, like in which you have a spinner in here. Then the angles between them is 120, since you have a spinner, as we told you. And the one that is above and down is 90 degrees. And that's why you have two types, or let's say two forms of angles. So those are the geometries in here.